The conjunction between big data and machine learning provides assessment of food security after natural disasters. For those countries where agricultural resources are a key driver of economic growth. Therefore, we aim to fulfill the necessities of rapid food security and management after a natural disaster. To do so, we propose a framework that uses two supervised deep convolutional neural network to locate, classify, and further optimize paths for the collection and transportation of these natural resources. The first model performs the task of object localization to localize and classify trees. Additionally, we propose auxiliary methods to determine the density of each of these trees and rendering them in density maps to quickly comprehend the condition of the agricultural site. The second model performs a semantic segmentation to mask the streets from the aerial imagery for transportation purpose. Ultimately, we introduce methods to optimize harvesting of fruits based on specific scenarios, such as maximum time, path length, and location of warehouse and security points.
The first model is a multi-layer convolutional neural net. It takes an RGB image as input and gives a 5x5x8 tensor as output. The model retrieves the location and classes of trees in pixel space. These trees and their locations can be compared with their error states to understand better how local agriculture and food security were affected. This information can directly inform and accelerate subsequent relief efforts. In the video, we are seeing how the platform should work. It automatically locates and classifies each tree. We aim to create a web interface where users can upload their imagery and have this result. All the trees are localized with a bounding box representing the class they belong. The F1 score of the model is 89%. This was obtained by getting an average from precision in locating and counting, which is 80%, and the accuracy in recall for type of trees, which is 98%. In order to validate our approach, we applied the tree recognition module to an aerial imagery from another site. The success retrieve of trees from this imagery indicates that our tree recognition module is able to work in different scenarios. Density maps can provide valuable insight in agriculture because it can communicate clearly the characteristics of geodata. These results will also be provided in the web interface. A density map for each class of trees is provided, allowing to understand the condition of these resources.
The second neural net model consists of convolutional and deconvolutional layers. The model takes an RGB image as the input and produces an equal-size image that is pixel-wise colorated based on semantic labels as the output. All the pixels that have the same label are colorated identically. The model was trained with these 6 categories: streets, buildings, cars, trees, low vegetation, and background. The result of the model allows us to identify local transportation infrastructure, buildings, and open areas, and in the scenario of natural disasters, to understand the impact onto them and inform the proper plan to distribute aid across affected areas. By applying a filter, we could mask the streets and see clearly its structure. Later, the street layer can be used on the further analysis. Instead of trying to extract precise lines to represent the streets network from the image, we assume that the distance between two disconnected street segments has a strong relation with the probability of them being an entire street. The shorter the distance, the higher the probability. A random subsampling process is made on the result image. Each pixel that is labeled as a street has a certain probability to be chosen as a node. Then a Delaunay triangulation is made on top of the nodes to represent the whole street network. The edges are weighted so that shorted edges gain higher priority. By overlapping the density map and the street networks, the nodes of the network are weighted by a number of trees within their reaches. Now, the shortest path between 2 points of the network can be calculated by optimization algorithms.
We proposed 2 types of query process. One is to maximize the number of crops to harvest with the length of travel distance limited, and the other is to minimize the travel distance with the number of crops to harvest limited. In future work, inspired by the success of this experiment, we could apply this approach to any question regarding localization, classification, or transportation of resources. An example could be the assessment of damage in buildings, for example, low, mid, and high damage after a natural disaster. Another application could be for monitoring the type of rooftop materials to determine the social condition of some region of interest.